So in this lecture, we're going to look at an application of Bayes' theorem and kind of by extension conditional probabilities to a situation that occurs a lot in medicine where you have a test whose results aren't completely reliable. Right? In a situation like this, there are two factors we have to consider. First, whether or not the person being tested actually has the disease or doesn't. And second, whether or not the test result was positive or negative. And so these options give us four possibilities. Two of these are desirable, right? These are the ones where the outcome matches the patient's condition. They have the disease and test positive, or they don't have the disease and test negative. The other two options are undesirable. The case where the patient gets a positive result but doesn't have the disease is called a false positive. And the case where the patient gets a negative result but does have the disease is a false negative, right? And in probability terms, a false positive will be represented by the probability that a person tests positive given that they don't have the disease. And a false negative would be represented by the probability that the patient tests negative but does have the disease. Okay, so let's look at a practical situation where we can use Bayes' theorem and conditional probabilities to analyze the likelihood of some of these situations. So I've got a question here for us, and it's a little busy, so if you want to pause and read this through, that's great. What we have is a test for a medical condition that's pretty rare, only occurs in 1 out of 10,000 people. And we know some things about the results. The proportion of people who test positive but don't have the disease, that's a false positive, is 1%. And we know that the proportion of people who test negative but have the disease, that's a false negative, is 2%. And what I want to know is what's the probability that a randomly chosen person who tests positive has the disease, and what's the probability that a randomly chosen person who tests negative doesn't have the disease? In other words, I want to find the probabilities that the test gets it right. Okay, so before we jump into numbers, when I'm looking at an even marginally complicated probability question or one that has more than one event, I think it's helpful to explicitly state what the events are. Right, so I'm going to let P be the event where the patient tests positive, and I'm going to let H be the event where the patient has the condition. So I'm also going to want to talk about when the patient tests negative. Well, that's the complement of P. So I'm going to write that P with a bar over it. And I'm also going to talk about the situation where the patient doesn't have the condition. That'll be H bar. Okay, so what information can we pull from the question here? The probability of H, the probability that a patient has the condition, that's just 1 over 10,000, which is 0.0001. And that 1%, that is the likelihood that a person who doesn't have the disease, that's what we already know, right? We're assuming that the patient doesn't have the disease. We have that information. So that's the part that goes after the bar in the conditional probability. And we're looking for the probability that they tested positive, so that goes in front of the bar. Right? So the probability of P given H bar is 0.01. When similarly, the 2%, we know that the patient has the condition, and we're talking about the probability that they test negative. So that's P bar given H, that's 0.02. Okay, so what are we actually trying to find? Right? What's the question asking for? Well, the first part is asking for the probability that the patient has the disease given that they tested positive. So that's H given P. And the second part, what's the probability that they tested negative? So we know the test result, and we want to know the probability that they don't have the disease. So that's H bar given P bar. Okay, before we move on, I want to grab two more probabilities from the 0.01 and the 0.02. I want you to think about what is the complement of P given H bar? Well, that's going to be P bar given H bar. The complement rule says that's 1 minus 0.01, which is 0.99. Similarly, the complement of P bar given H is P given H, and again, the complement rule tells me that that is 0.98. Okay, so let's go to the next slide. I'm getting a little bit out of room. Okay, so I've got all my information summarized here. All the stuff that we've calculated is up in the upper right. And the two things that we want to calculate are on the left. So, I've got Bayes' rule here for the situation where we have our sample space partitioned into two events, J1 and J2. And what I want you to notice here, but before we jump in and start applying the formula, if you look at the probabilities that we know from the question, they're all a test score given a condition. What we've been asked to find is the probability of a condition given a test score. Remember, I talked about this at the very end of the last lecture. This is what Bayes' theorem is helpful with. It helps us to reverse the order of the things in a conditional probability. Okay, so what I'm going to do, I'm going to go for the first one first, H given P. So what I'm going to do is I'm going to substitute H for J1, P for G, and J2, that's the other side of the partition, right? So if J1 is H, then J2 is H bar, right? So I go ahead and pause if you like, and confirm that I made all those substitutions correctly, because from here it's just a numeric problem. I'm going to take the probabilities that we calculated previously. I'm going to substitute them in here, and that gives me the probability of the patient having the condition, given that they got a positive result, is 0.0893. In other words, this is the probability that a positive test result is correct. And that may not seem like a very good answer. May not seem like a very good result. But I ask you to bear with me for a minute, right? Let's calculate the second probability that we were asked for. Then we'll come back and talk a little bit about the implications of the results. Okay, so I'm going to do the same thing here. I'm going to substitute H bar for J1, P bar for G, and that's going to make G2 the complement of J1. So that's the complement of H, which is just H. If I make that substitution, we get this. Again, you're welcome to pause and work through that for yourself if you like. But again, now it's just a numeric problem. I'm going to substitute in my numbers, and I'm going to get this very different result, 0.99998. Right? So again, remember what we were asked for here. This is the probability that a negative test result is correct. Okay, so let's think about some of the implications of this. Okay, so let's take a look at these results, because at first glance, the second one, the 0.99998, yeah, okay, that seems pretty good, right? It's getting it wrong, what, 2 times out of 100,000? Okay, that's a pretty decent result. That 0.0893, yeah, not so good. Right, but let me put a situation out there, all right? Let's say that this particular test is inexpensive. And let's say there's another test that is much, much more likely to get the positive result correct, but it's really expensive to do. Okay, then I'm going to say that this is a good situation. In this kind of medical testing, there's two things that we would really like to have. We would like to have a test that A, is inexpensive, and B, that minimizes false negatives. Yeah, because false negatives are the worst case. That's when you tell a patient that they don't have the disease, but they do. So they're not getting treatment for a potentially serious condition. Right? So our test checks off both of those boxes. Right? It's inexpensive, and when it gets a negative result, that negative result is almost always correct. Right? So it would be advantageous to use this test first, weed out the people who don't have the condition at all, and then do the second, more expensive test, only in the case where we need to confirm the first one. Right? So essentially that second, more expensive, more reliable, more likely to get a correct positive result test is kind of just the first step in the treatment. Right? So there are situations where Although that 0.0893 may seem pretty bad, there are situations where this would actually be a good test to put into use. Okay, so where are we going next? The next thing we're going to talk about is something called independence. Right? We'd like to know when one event is independent from the other, in the sense that uh, when one event happens, it in no way influences the second result. That's what we mean by independence. Just kind of at a high level. We're going to look at that a little more numerically in the next lecture.